100 prisoners, 100 boxes. Each prisoner gets to open 50 of them. If every single prisoner finds their own number, they all go free. If even one fails, nobody does. Play it the obvious way, and your odds are this. Play it the right way, and your odds are this. Same prisoners, same boxes, same 50 openings each. Nothing has been added except a decision about which boxes to open, and the probability of survival has moved by 30 orders of magnitude. That gap is not a trick. There is no communication, no marking of boxes, no cleverness with the rules. It comes entirely from a fact about permutations that most people have never had a reason to notice. A room contains 100 boxes in a row, numbered 1 to 100. Inside each box is a slip of paper with a prisoner's number on it. 100 slips, 1 per prisoner, distributed uniformly at random. The prisoners enter one at a time. Each may open at most 50 boxes in any order, choosing as they go. Each sees what they find. Then the boxes are closed, the room is restored exactly as it was, and the prisoner leaves, with no way to signal anyone still waiting. They can agree on a strategy beforehand. That is the only cooperation allowed. Everyone lives only if everyone succeeds. The natural strategy is to open 50 boxes at random. A single prisoner does fine. 50 boxes out of 100, so the chance of finding your own number is 1/2. That is not the problem. The problem is that everyone has to succeed at once. Under random choice, the prisoner's outcomes are essentially independent, so the survival probability is 1/2, times itself, 100 times, 10 to the negative 31. To calibrate that, if the 100 prisoners had run this once per second since the universe began, they would still, overwhelmingly, never have won. Not once. And here is the thing that should bother you. Every prisoner is playing a fair coin flip. Individually, nobody is doing anything wrong. The strategy fails not because any single choice is bad, but because 100 independent coin flips never land heads together. So the fix cannot be to make any individual prisoner luckier. 50 boxes out of 100 is 1/2 no matter which 50 you pick. That ceiling is fixed. The only thing left to change is the correlation between prisoners. We need their failures to happen together so that the winning case is one big lucky event instead of 100 small ones. Here it is, and it takes one sentence. Prisoner K opens box K first. Whatever number is inside, that is the next box they open. Repeat until they find their own number or until they have opened 50 boxes. That's all of it. No randomness, no agreement beyond this rule. Watch what the chain does. Prisoner 7 opens box 7 and finds 34. Opens box 34, finds 61. Opens box 61 and finds 7. Their own number. The chain closed. And notice it had to close, and it had to close on 7 specifically. The arrangement of slips is a permutation. Box I points to the prisoner whose slip is inside it. Following the chain from box K is following that permutation forward from K. A permutation of a finite set decomposes into disjoint cycles, and the only way back into box K is through the slip numbered K. So the chain starting at K is exactly the cycle containing K, and the last box before it repeats is the one holding slip K, which gives the whole thing away. Prisoner K succeeds if and only if the cycle containing K has length at most 50. Not usually, always. It is a deterministic consequence of the arrangement. And now the correlation we were looking for is right there. Every prisoner is asking about the same object, the cycle structure of one permutation. If that permutation has all cycles of length 50 or less, then every prisoner succeeds. If it has one long cycle, everyone on that cycle fails together. 100 coin flips became one question. So, what is the probability that a uniformly random permutation of 100 elements has no cycle longer than 50? Go at the complement. Count permutations containing a cycle of some specific length k, where k is greater than 50. Choose which k elements lie on that cycle. See at 100 k ways. Arrange those k elements into a single cycle, k1 ways. Arrange the remaining elements however you like, on 100 k ways. Multiply. Divide by 100, total permutations, and the probability that a cycle of length exactly k exists which is a startlingly clean result. The factorials annihilate completely. Now the step that makes this easy. Since k is greater than 50, there is only room for one such cycle. 2 cycles of length 51 or more would need over 100 elements. So these events are disjoint, and we may simply add them, harmonic numbers. And Hn grows like ln plus the Euler-Mascheroni constant, which cancels in the difference, therefore 31%. And look at what the answer does not contain. No 100. The approximation is ln2 for any number of prisoners, 1,000, 1,000,000, as long as each may open half the boxes. Scale the problem up arbitrarily, and the survival probability does not decay. It sits at 31% forever. That is the genuinely strange part. The random strategy gets worse exponentially. This one does not get worse at all. Derivations can be wrong. Let's run it. 1,000,000 trials. It converges to 3069 against a predicted one, minus ln2 of 3069. The derivation holds. It is tempting to file this under cute puzzle. I'd file it somewhere else. The random strategy treated 100 prisoners as 100 independent problems, and independence is exactly what kills you when you need every one of 100 things to go right. The cycle strategy did not improve anyone's individual odds. Prisoner 7 still finds their number about half the time. What it did was make the failures land together. That move, restructuring a problem so that the bad outcomes coincide rather than accumulate, is not a puzzle trick. It is the entire logic behind why redundant systems are built to fail in correlated ways on purpose, and why a portfolio of independent small risks behaves nothing like one large one. The odds did not change. The shape of the randomness did.